Hi, this short video will take the place of our weekly chat, which didn't work out real well last week. So I'm going to go over the material in Chapter 16. We're going to learn about confidence intervals for proportions. And when we talk about a confidence interval, if we need to remember the sampling distribution model that we had for a proportion that we learned about in Chapter 15, and if you remember, it talked about the standard deviation of that sampling distribution being calculated with this formula. The problem is we don't know p. We're using our sample to estimate p, so we're going to use the formula with p hat in place of p, and we're going to call it the standard error, and that's the measure of variation that we're going to use for the sampling distribution of p hat. And if you remember your empirical rule, remember 68% of all samples are going to fall within one standard error of the true population parameter. And so here we're going to be talking about whether p hat is within one standard error of the true population proportion. And if we turn that around a little bit, we can also say there's a 95% chance that p is no more than two standard errors away from p hat. So if we reach out two standard errors, we can be 95% sure that p will be in that interval, p being the population proportion. And we call this the 95% confidence interval. Every confidence interval uses a sample statistic to estimate the population parameter, and that's what we call the point estimate. And each sample that we take is going to give us a different estimate of the population parameter, in other words, another statistic or point estimate. So the confidence that we talk about is in the process of constructing the interval, not in any one interval itself. So we expect 95% of all 95% confidence intervals to contain the true parameter that we're estimating. And this shows actually a pictorial of what that means. So this green line is the true population proportion, and we took 20 samples, let's say, all of the same size, calculated the confidence interval. The red dot is the point estimate. We notice that this interval does not capture the true population parameter. This one doesn't. This one doesn't. If we did 100 samples, 95 of them would capture the true population proportion, but 5% would not. And the problem is when we're doing this sampling idea, we don't know which proportion, which interval we're actually calculating and how it relates to the true population proportion. That's why the 95% confidence talks about the process of building it. Now, when we take the p hat, we put that at the center of the confidence interval, and we extend two standard errors on either side. We call that distance on either side the margin of error, and we can write a general form for a confidence interval as the estimate plus or minus the margin of error. The more confident we want to be, the larger the margin of error is going to be. But to be more confident, we're going to be less precise. The wider the interval is, the less precision there is in our estimate. And so there's always going to be a tension between certainty and precision, and you're going to have to determine in a particular situation what's more important to you. If we can increase sample size, we can also increase confidence and precision at the same time. So the choice of confidence is somewhat arbitrary, but again, keep in mind that tension. And the most commonly used intervals are 90, 95, 99, but we can use any confidence level. Now, technically, the two that we were talking about before in that standard error, margin of error formula is actually, if you look at the normal distribution, it's a little bit smaller than 2. To capture 95% of the area under the curve, we only have to go 1.96 standard deviations on either side. But we'll be using technology, so we won't have to worry so much about that. Now, as we move into inferential statistics, all the different distributions we're going to work with have assumptions and conditions that we need to check. And for this particular situation, for the one sample proportion, and we're trying to do the confidence interval, we want to talk about whether or not the observations are independent of one another. And that would come along with a randomization concept. So if it was a random sample or a randomized experiment, we can assume that the independence will go along with it. 10% condition is the sample size has to be less than 10% of the population. And lastly, the sample size assumption. Our sample size needs to be large enough to use the central limit theorem. And for this particular distribution we're using here, we're going to check successes and failures. We want to expect at least 10 successes, which means sample size times p hat must be greater than or equal to 10, and at least 10 failures. So sample size times 1 minus p hat must also be greater than or equal to 10. Remember, the successes and the failures added together give us the whole sample size. Here's two sources you might want to take a look at for the quality online survey and poll data. When you're looking at a survey or poll report, you want to look for details about the survey methods. How was the sample size, what sample size was used, how was the sample obtained, and what's the margin of error. So let's take an example. We asked 510 people, do you believe that the death penalty is applied fairly? 58% of the people said fairly, 36% said unfairly, and 7% said I don't know. And we want to calculate a confidence interval for the proportion who answered fairly. So we want to think about what we're working with here, and we want to find a 95% confidence interval for the population proportion of people who feel the death penalty is applied fairly. Okay, the model we're using is the one sample, one proportion Z interval. We want to check the assumptions and conditions. This was a Gallup poll, so it's probably random. Less than 10%, yeah, 510 would be less than 10% of all Americans. Success failure, we're going to take the 58% that was that answered fairly in the survey times the sample size. We get the successes, 296, and then we take 510 times 1 minus p hat, and we get 214. Notice this plus this equals the 510, so we can use the normal model. Okay, so mechanics. What you need in StatCrunch to use StatCrunch is N, and you need the number of successes. So in StatCrunch, select Stat, Proportion Statistics, one sample with summary, add your successes, 296, and I have a window here to show you what it looks like. Put in the successes, the sample size, and then down here, next week we'll learn about the hypothesis test, but for right now, confidence interval for the proportion, and then put in the confidence level, and we're doing 95%. And then compute. So here's your results, here's your successes, here's your observations, here's your p hat, standard error. So here's my confidence interval from about 53.8 to 62.3. Margin of error, 62.3 minus 53.8 divided by 2, 4.25, or about 4.3%. So the conclusion, I'm 95% confident that I could either say this that's written here, or the true proportion of U.S. adults who think the death penalty is applied fairly is between 53.8 and 62.3. Let's try this one. A catalog sales company promises to deliver orders on time placed on the order internet within 3 days. Follow-up calls to some randomly selected customers given 95% interval is 84 plus or minus 4. Select the statement that best describes the confidence. Now remember, first of all, the interval, we can add and subtract the margin of error, so we know it goes from 80 to 88. One can be 95% confident that all random samples of customers. That's not a correct interpretation. This one's talking about the samples, the 95%, rather than confidence. This one says one can be 95% confident that the true population percentage of orders placed on the internet that arrive within 3 days is between 80 and 88. That sounds really good. This one says between 80 and 88% of all orders arrive on time. It's not talking anything here about confidence. So the correct answer for this one would be the third choice. An insurance company checked police records for 565 accidents to determine the proportion of accidents in which the driver was a teenager. They calculated the interval as 13.1 to 19.5. What's the margin of error? Okay, upper minus lower, half the width of the confidence interval, so 19.1 minus 13.1 divided by 2, 6%. What's the point estimate for the percentage of accidents in which a teenager was the driver? The point estimate is the sample estimate that was calculated from the 565, and the point estimate, remember, is used to create this interval, so it sits right in the middle of the confidence interval. And you can find it by adding the two endpoints and dividing by 2. Also, you have the margin of error, so you could also take that plus the lower bound, and you would get the same point estimate. If the insurance company wants to be more confident, would the margin of error increase or decrease? Okay, if we want to be more confident, remember the interval is going to be wider, so the margin of error would increase. Okay, you stop by your local independent coffee shop on your way to school. When standing in line, you notice 85% of 20 customers are texting. Assume the customers form a reasonable sample of all potential customers. If we tried to make a confidence interval for the proportion, did we satisfy all the conditions and assumptions? Random, it says we can assume they're a reasonable sample, so that means yes. So therefore the independence is met. Less than 10%, 20 customers should be less than 20 or 10% of all customers. Success failure, so n times p hat, so 20 times the 0.85 gives us 17, that's good. But now when I take n times 1 minus p, I only get 3, and that's less than the 10 that I need in order to apply the sampling distribution for the proportion and the central limit theorem, so I can't proceed on this problem. Okay, and I'm going to stop here. I only have a certain amount of time on this video, so you can work through the last few problems on your own.